Think about the biology of a dividing human cell, the precise electrical pathways inside a microchip, and the heavy bulk of an industrial battery. On the surface, they share absolutely nothing in common. But if you look close enough, these three completely different physical realities are built on the exact same chemical foundation. Looking at this generalized atom from group 14, you see an arrangement with exactly 4 valence electrons in its outer shell. Because of these 4 electrons, every element in this column shares one trait, the capacity to form 4 stable covalent bonds. Which leaves us with a paradox. If the fundamental math of their chemistry is identical, why do the actual materials look, act, and feel so completely different in the real world? A periodic column functions as a descending physical gradient. By simply adjusting one physical dial, the size of the atom, the nature of matter transitions from one extreme to another. This diagram highlights carbon at the very top. Its atomic radius is incredibly small compared to elements beneath it. Because the atom is so compact, the nucleus sits right next to the outer electrons, holding them with an absolute iron grip. That unyielding grip means carbon is a strict nonmetal. It refuses to let its electrons flow freely, forcing it to form rigid, incredibly strong molecular chains instead. This tight atomic structure is the exact reason carbon fiber is so famously strong and flexible, and why carbon provides the necessary stability to serve as the structural backbone of all organic life. And when you place those tightly bound carbon atoms under immense geological pressure, they lock into a crystal lattice to form diamonds, the hardest naturally occurring material on the planet. At the very top of the gradient, extreme atomic tension yields the rigid, non-metallic structures required to build both biological life and our most durable materials. But as we step down the column to silicon and germanium, we add extra layers of electrons. The overall size of the atom expands. When we compare the compact carbon atom to these larger silicon and germanium models, you can see the effect. The distance from the center weakens the magnetic pull. Electronegativity drops, and the nucleus can no longer hold on to its outer layer quite as tightly. This structural expansion pushes these elements into a new phase, the metalloids. They exist in an unstable, in-between state, behaving neither as a pure nonmetal insulator nor a pure metallic conductor. Silicon is incredibly common. It's the second most abundant element in the Earth's crust, and for centuries its main industrial application was the art of glassmaking. But that unique in-between electrical behavior holds a specific power. Because they sit right on the fence between resisting and conducting, silicon and germanium act as perfect semiconductors. We can actually manipulate them to control the exact flow of electricity. That specific capability allows engineers to build microscopic logic gates that can switch currents on and off billions of times a second, birthing the entire modern computing age and global fiber optic networks. The middle of the periodic gradient provides the exact electrical instability we needed to construct the digital architecture of human civilization. Descending further brings us to tin and lead. By the time we reach this far down the group, the atomic size is massive compared to the elements at the top. Looking at this much larger atom model, the electronegativity is now incredibly low. The nucleus is too far away to keep a grip on its outermost shell. The electrons detach entirely into a freely flowing sea, transitioning these elements into pure, true metals. This enormous size also triggers a chemical anomaly. The standard +4 oxidation state that defined the rest of the group begins to break down, replaced by a more stable +2 state, particularly in lead. This shift alters how the elements bond at their most basic level. Because of its free-flowing electrons, tin becomes highly malleable and entirely metallic, making it the perfect anti-corrosive coating for millions of tons of industrial steel. Lead takes this a step further. Its extreme density and pure physical weight make it highly reliable for absorbing and storing electrical charges in heavy industrial batteries. And that exact same immense density is thick enough to stop high-energy radiation in its tracks, providing essential shielding in nuclear laboratories. We can push this logic to its absolute breaking point with fluorovium, a synthetic, highly radioactive metal with a fleeting half-life that humans can only manifest for fractions of a second inside a lab. At the massive scale of the bottom elements, the delicate structural complexity of carbon and silicon is traded entirely for raw, heavy metallic durability. This graph maps out that entire vertical descent, revealing group 14 as a perfectly continuous physical spectrum. The governing rule is strict and predictable. As the atomic size steadily increases down the column, the metallic character must inevitably increase right alongside it. The simple mathematical constant of 4 valence electrons acts as a highly adaptable toolkit for the universe. By adjusting a single variable, the sheer physical size of the atom, the exact same chemical math scales seamlessly from the delicate biology of life, through the precision of digital technology, straight into the sheer weight of heavy industry. Chemistry operates on rigorous, beautiful logic. The Group 14 column proves that the wildly diverse materials of our world aren't accidents. They are exactly what happens when you pull the precise, predictable physical levers of reality.